Hello and welcome to today's lesson on ohmic conductors. Today we will discover what ohmic conductors are and then identify some examples. Once we have done this, we will learn about the current versus voltage graph, or IV graph, of ohmic conductors and how to plot it. So far we have delved into Ohm's law. You have learned that Ohm's law expresses the relationship between current, voltage, and resistance in an electrical circuit as V equals I multiplied by R. Building on this, we will explore an important type of component, ohmic conductors. Let's get started! In the previous lesson, we covered Ohm's law. According to Ohm's law, the current, I, passing through a resistor at a constant temperature is directly proportional to the potential difference, V, across it. This relationship can be expressed simply as I equals V, divided by R, where R is the resistance. However, this law doesn't apply to all resistors. Ohmic conductors are specific types of resistors that do obey Ohm's law. The key feature of ohmic conductors is that their resistance remains constant, provided the temperature does not change. Ohm's law can be rearranged to R equals V divided by I. This means that, for an ohmic conductor, if the current through it increases, then so does the voltage and vice versa, maintaining the resistance at a constant value. Some common examples of ohmic conductors include metal wires, fixed resistors, and variable resistors set to a specific value. Let's look at metal wires first. Typically, a metal wire will behave as an ohmic conductor provided it remains at a constant temperature. Next is a fixed resistor. This is a resistor with a set resistance value that doesn't change under normal operating conditions. For instance, if you have a fixed resistor marked as 5 ohms, its resistance will remain around 5 ohms at room temperature. Our last example is a variable resistor. Unlike a fixed resistor, you can adjust a variable resistor to different resistance values. However, once set to a specific value, it behaves as an ohmic conductor and maintains that specific resistance as long as the temperature stays consistent. For instance, if you set it to 5 ohms, it will remain at 5 ohms until you change it again. During the period it is set at 5 ohms, it behaves as an ohmic conductor. To better understand ohmic conductors, we can look at their current voltage or IV graph. Ohm's law tells us that I equals V divided by R for a given resistor. Here, the resistance remains constant at a particular temperature. Let's translate this into a graphing context. When we plot the current, I, on the y-axis and potential difference, V, on the x-axis, the formula I equals V divided by R can be rearranged as shown. This corresponds to the equation of a straight line, y equals mx plus c. In this scenario, y, current I, is plotted on the vertical axis. X, potential difference V, is plotted on the horizontal axis m. The gradient is 1 divided by R. C, the y-intercept, is 0, since at 0 volts there should be 0 current. This means the graph of an ohmic conductor will be a straight line passing through the origin, 0, 0. The line's slope, 1 divided by R, will be constant and will determine how steep or flat the line is. For example, a smaller resistance results in a steeper gradient, indicating that even a small voltage will produce a relatively large current. On the other hand, a larger resistance results in a flatter gradient, showing that a larger voltage is required to produce the same current. In today's lesson, we delved into the concept of ohmic conductors and how they behave under different electrical conditions. We learned that ohmic conductors are materials that obey Ohm's law, meaning their resistance remains constant as the voltage across them changes. Some examples of ohmic conductors are metal wires, fixed resistors, and variable resistors. We then learned that the resistance remaining constant as the voltage across them changes results in a linear relationship between current, I, and voltage, V. This can be represented by a straight line passing through the origin on an IV graph. In the next 2 lessons, we will look at the IV characteristics of 2 non-ohmic components, lamps and diodes.